Good morning, everyone. Welcome to the Monday's class for Caltri. So, as I promised, today and tomorrow classes will be conducted online. So, meaning I will upload videos to Blackboard. Okay. So, uh, today we are going to cover section 6.4 Green's theorem. Now, what Green's theorem do is it connects the line integral with double integral. So it's kind of like line integral connects line integral with double integral. So in a sense, if you want to do a line integral, you can convert it into a double integral, or if you want to do a double integral, you can convert it into a line integral. So that's what we are going to do here. Now, the Green's theorem says, okay, it has two conditions. We have to have an open, simply connected region, meaning it should be something like this, excluding the boundary. Since it is open, it does not contain the boundary. So we are interested in this region. It is open, simply connected means it does not have holes in it. And the boundary, so this is D. The boundary of D is piecewise smooth, simple, closed, oriented clockwise. What does that mean? Piecewise smooth, of course, it should consist of finite number of smooth curves. It should be simple, meaning it should not cross itself. Closed, initial and terminal should be the same, oriented clockwise, counterclockwise. So it has a direction. Now, D is the region inside, then the boundary of D is the border of that region. Now, if you have all these conditions, even though I said it's all these conditions, it's not much to ask. We have three equations that can be used. So number one is the most general form, and it can be used to create 2 and 3. Now, it says the line integral of f dx g dy over the closed region C is equal to the double integral over the region D, where it is you take the component for y and differentiate it with respect to x. You take component of f and differentiate it with respect to y and take the difference. Now the catch is f and g has to have continuous partial derivatives. Okay. Now this is the general form. For our purpose, we need we looked at two types of line integrals. Okay, actually two types of vector line integrals, circulations and flux. So the second one is for circulation. So it's called circulation form. Circulation form of the Green's theorem. It says the circulation of F along C. Now we know it is P dx plus Q dy. So using Green's theorem, we can say it is the double integral of qx minus py. So it's so if you want to get number 2 from number 1, you pick f equals p and g equals q. This is the circulation form. Then we have flux form. The flux through the closed curve C can be written as negative q dx plus p dy. We already know this from a previous section. Now using f equals negative q and g equals p, we get this is the double integral px plus qy. So we will be using number 2 and 3 throughout this section. Okay, so now before doing few examples, let me go through the intuition behind this. So it's always easier to think of the flux, because remember, flux of a counterclockwise oriented curve is the amount passing out from the curve. Okay, so let me draw a picture here. Let this be a curve oriented counterclockwise. Then the flux is amount passing through, actually passing out of this curve. So the flux is the amount going out. So you can think it as a water flowing out of this curve. Now you can imagine there is a spring here inside. So the water is coming from that spring and it is passing through this curve out. So flux is the amount passing through. Right. So what we can do is, okay, first we are going to fix a y value and look at the x coordinates or p coordinates. Let's say this is p0, p1, p2, p3. So now I took a horizontal line, meaning y is a constant. So I can think of the partial derivative with respect to x. Now the integral of the partial derivative with respect to x is, using fundamental theorem, it is the terminal value minus the initial value, p3 minus p0. Okay, p3 minus p0 is in the picture. P3 we have that, minus p0 is the opposite direction. Now you can see p3 minus p0 gives you the amount going out on the right and the amount going out on the left. Now if I do the double integral, I'm going to add such amounts. So it gives all the flux going right plus the flux going to the left. So it is flux going right plus left. So the double integral of p sub x gives you flux going from right side of the curve and the left side of the curve. Similarly, the double integral of qy, you can use a similar idea, similar explanation to show that the double integral of qy is the flux going from top and going from bottom. That is the flux going out from top plus the bottom. So if you add these together, you get the total flux. So total flux is the double integral of px plus the double integral of qy. Okay, so we get the required formula using this argument. So you can use a similar argument to show the circulation, but in my opinion, flux is the easiest to visualize. Again, you should think as there's a spring in the middle of the region, water is coming out, and water passes through this curve, and that is the flux amount. Okay, so let's do a few examples using this Green's theorem formulas. Example 38. Calculate the line integral over the rectangle C with vertices given here, oriented counterclockwise. Okay, so let's draw a picture. 1 1 4 1 4 5 and 5 1. So this is the rectangle we are interested in. And it says it's counterclockwise. So this is the region C, curve C. Now we need to calculate the circulation. So what Green's theorem says is, instead of calculating circulation, you can do the double integral. Now the reason for doing this is, okay, if I want to calculate the circulation, you should remember that you have to rewrite this curve as 4 curves, C1, C2, C3, C4. Then you parameterize each curve and you do 4 integrals to calculate the circulation. Now instead of that, we can do a single double integral. That's the power of Green's theorem. So what Green's theorem says is, instead of finding the circulation over C, we can do the double integral over D. Now this is P, this is Q. By Green's theorem, this is equal to the double integral over D Q sub x minus P sub y dA. Derivative of Q with respect to x is 0. Derivative of P with respect to y is x squared. Okay, now this can be easily calculated because the region is x in between 1 and 4, y in between 1 and 5. So this is the double integral, x going from 1 to 4, y going from 1 to 5, negative x squared dy dx. Now we know how to calculate this. You can rewrite this as a product of two integrals, and doing so you should get the answer negative 84. Now if we were to just integrate the given curve, then you will have to do 4 parameterizations and 4 integrals and finally add them. But using Green's theorem, you can do it within like 3-4 steps. That's the power of Green's theorem. Okay, so let's do another example. The next example is calculating the area of an ellipse. Now, sometimes it is harder to do the double integral. Therefore, we can use Green's theorem to go back to the line integral. So for this example, the double integral is not straightforward. So what they are asking is the area of this curve. So they are asking for the area of the yellow color region. Now the double integral is not easy to calculate. So the double integral is not, let's say, straightforward. To evaluate. Therefore, we are going to use the reverse direction of Green's theorem. So use Green's theorem to calculate the double integral over this region. Now, to find the area, you evaluate double integral of 1. Now, remember, now to use Green's theorem, we should have q sub x minus p sub y. Now that means q sub x minus p sub y should be 1. So it's a choice. So let's choose. Q equals x over 2. When you differentiate with respect to x, you get half here. And let's pick p equals negative y over 2. When you evaluate, this becomes negative half. So half minus a negative half becomes 1. So we just picked p and q so that the Green's theorem, when I apply Green's theorem, you have 1 in the integral. So that is the area. Area is double integral of 1. Okay, so now by Green's theorem, this is equal to the circulation of the boundary of the region, p dx plus q dy. Now we know what p and q are. So it is the circulation, the boundary of the region, x over 2 dx minus y over 2 dy. Right. Now we need to evaluate this integral. Now To do that, it's a line integral. So let's parameterize the given ellipse. So the ellipse can be parameterized by, so it is the standard parameterization: a cosine t, b sine t, where t going from 0 to 2 pi. Since the formula of the ellipse is x squared over a squared plus y squared over b squared equals 1, pick x equals pick x equals a cosine t, y equals b sine t. So this is the standard parameterization of the ellipse. So let's evaluate the integrals. So okay, so area is the integral we already found, which is, now the parameterization goes from 0 to 2 pi. X is a cosine t x over 2, and dx is what? Dx is you get oh my bad, so p is negative y over 2. So let me change this slightly. So we found p is negative y over 2, so this should be negative y over 2. Q is x over 2. So this should be negative y over 2. This should be positive x over 2. Right. Okay, now we can write the correct one. Negative y is b sine t over 2. Dx is derivative of the x component, negative a sine t, plus x over 2. So x is a cosine t over 2, derivative of y, which is b cosine t. You can take half out as a common factor, you get, and of course you can take ab also as a common factor, you get the integral of sine squared t plus cosine squared t, which is 1. So the integral is 2 pi, half ab times 2 pi. So we get ab pi. The area of the ellipse is given by ab pi. Right. So if the double integral is harder to evaluate, use the reverse direction of the Green's theorem. If the line integral is harder to evaluate, use the forward direction of the Green's theorem. Okay, so let's do one more example. A short example, example 41. Calculate the flux of this function x comma y across the circle of radius r with center at origin. Now we know how to find the value because now xy is a radial field, so you are adding, so the field does not have a circulation part, circulation is 0, so it's only adding flux to it. Okay, so uh, now instead of using the straightforward calculation, we can use the flux form of Green's theorem. So the flux is given by this formula. Now by Green's theorem, it is the double integral over the region of P sub x plus Q sub y. Okay, so P sub x is, so P is the first coordinate, Q is the second coordinate. So it is 1 plus 1. So 2 times the double integral of dA, which gives you the area of the region D. Now it is a circle of radius r, so the area is pi r squared. So the answer is 2 pi r squared. Okay, so let me stop the first video here and we'll continue from this point in the second video.